We are now going to do part B of example 1. Again, the question says there are initially 2,200 of a certain mutation of Faecium in a petri dish. The bacteria has a growth constant of K equals 0.027. We're now going to answer part B, which asks at what point in time where there'll be a million bacteria. At what point in time means that we need to solve for a particular t-value. We are given that there will be a million bacteria, so that will give us our population of bacteria. We're going to follow the same steps as we've done before. We're going to write out our growth formulas for exponential growth. Now, since this question asks at what point in time where there will be a million bacteria, which formula do you think we will be using? In fact, since it's not asking about a rate, it's giving us an amount and asking about a time, we will be using the population equation. Remember, we did a proof on this. You can derive this rate and use separable differential equations to get the population formula or the exponential growth and decay formula. Step 2 is we're going to write out what we know. We know that K is 0.027. We know there's initially 2,200, so P0 is equal to 2,200. Again, you could use A0, meaning the amount of bacteria. It doesn't matter. We know that there's 1 million bacteria, so we're going to set our general P equal to 1 million. For this particular question, we need to solve for time. So T is what we're solving for. Fortunately, if you write everything out and write your equation out, you should just have one variable to solve for, which you will see now. Here's our formula. We're going to rewrite it. Again, the way to read this formula is the population is equal to the initial population times e to the kt, where k is the growth constant. They gave us the population was 1 million. We were told that the initial population was 2,200. E is a constant, so it remains the same. K is our growth constant of 0.027. Voila. We've plugged in everything we need to know except for our t-value, which we can easily get by itself. This t, again, will tell us when there's 1 million bacteria in the petri dish. In order to solve this, you can see that right off the bat, you need to divide both sides by 2,200, which is exactly what we're going to do first. Now we have 1 million over 2,200 equals e to the 0.027t. I like to just leave it this way because I can plug it into my calculator that way. Next, we're going to take the natural log of both sides. When we take the natural log of both sides, the e cancels on the right, and I'll just kind of shorthand show that over here. I'm not going to write the whole thing out. When we take the natural log of both sides, the e over here is going to cancel, and we're left with the natural log of 1 million over 2,200 is equal to 0.027t. Finally, we're going to divide both sides by 0.027, and t is equal to the natural log of 1 million over 2,200, all of that divided by 0.027. Plug that into your calculator, and you get a time, let's use red since we were using red before, of 226.64 hours. This is how long it's going to take for there to be 1 million bacteria. Now that's actually not that long of a time. If we convert that to days, we will take the 226.64 hours and divide the fact that there's 24 hours in a day. We end up with a mere 9.374 days for it to go from 2,200 to 1 million bacteria. Answering this verbally, it will take a little over 9 days, again that's our t-value, for the bacteria population to reach 1 million. And see folks, this is why viruses and bacteria spreading is such a serious thing, because it only took 9 days to go from an initial population of 2,200 bacteria to 1 million, just 9 days. And that can happen, and as you can see, as this growth constant increases, it's more rapidly going to reproduce, and it's going to reach that million mark even sooner. So even a small K value can have a drastic effect on the growth rate and the population of the bacteria. That's it for this particular example. If you have any other questions about it, let me know.